Hello and welcome back. We continue our repair of the great HP8082A pulse generator. In the previous episodes, we determined that a custom ECL IC had failed and we were missing one of its output pulses. But we designed an inverter gate that would allow us to recreate the missing DEL pulse out of the still working ND pulse by simple inversion. Now, all we need to do is create the PCB for our design. The difficulty here is that the circuit should have rise times below 1 nanosecond, requiring bandwidth in the gigahertz range. Therefore, we must employ small surface mount components and treat it as an RF design. I had previously used Eagle to design PCBs, but it has an atrociously bad user interface, and to add insult to injury, it has recently been acquired by evil Omnicorp, so now you need to pay to suffer. So instead, I switched to the free KiCad PCB design program for the first time. And I found it far better than Eagle for my amateur use. So back to our board design. You have to be a bit careful in your layout when designing at these frequencies. And before I go further, I need a disclaimer here. I am not an RF engineer, but I work for a company that specializes in very high-speed designs, and I rub elbows with the true RF experts, which are electronic magicians as far as I'm concerned. In the real world of microwave engineering, you'd simulate the heck out of your circuit using ANSYS HFSS or Keysight's ADS, for example. But these tools are far beyond the reach of an individual and need a supercomputing infrastructure to run on. So Samtech engineers in general, and Scott in particular, if you're watching this, please look away for a while. So back to our design. It has one RF input and two RF outputs using the vintage SMC 50 ohm RF connectors that are already present in my HP instruments. I need a control impedance transmission line from the connectors to the 50 ohm terminating resistors, which I have placed as close as possible to their respective transistors. There are several ways to do control impedance lines on a PCB, but here we can use the simplest one, a strip line over a ground plane. You simply adjust your trace width until its impedance is 50 ohms, and PCBWay has a neat little online calculator for this. So one problem when you try to do this on regular boards, which are pretty thick, like 63 mils or 1.6 millimeters, is that to get to 50 ohms, you have to make them really fat. So it takes about 121 mils or 3 millimeters to bring it down to 50 ohms. And you can tell that's what HP actually did. Look at those huge fat traces going to the connectors. So those are because they need to make them 50 ohms, and they are way too big for my design. So instead I went to a 4-layer stack-up, which has the two first layers very close together. If you look at the spacing between the top layer and the first embedded layer, it's only 0.11 millimeters or 4.3 mils. And that will allow me to make my traces of reasonable dimension. So here I put the 4.3 in. And now, to make my trace 50 ohms, I need about 7.5 mils. Another thing you want to do to prevent impedance discontinuities and reflections is to avoid sharp bends. And I found this little external RF plugin that would make smooth bends, so that was perfect. Most of the rest is common sense to avoid stray inductance and capacitance, and put things that belong together in close proximity, like bringing the two transistors in the pair close together around their common emitter resistance. The one thing you do not want too close together is the input from the output, so I arranged the circuit so that the input is actually a fair bit away. This will reduce the chance of feedback leading to an oscillation. Finally, the DC bias section is non-critical, so I put it down the corner back there. And besides the top layer, everything else is a pore, so here's the ground plane just underneath, so it's just ground everywhere, so there's going to be a well-behaved circuit with that much ground. Then I use the layer beneath that to do the -5 volts. and I added a capacitor for good measure. And the last layer had one layer too many, so I just put another ground there. So that's it. Alright, the PCB have arrived from PCBWay and also the parts from DigiKey. So thank you PCBWay, it's been a while we hadn't ordered anything. And here's the little board, so I splurged, it's a 4-layer board. So I could do the 50 ohm traces really small. And I also splurged, I got the, how do you call them? The masks for the solders, the stencils. Also got some of, actually all of the parts. These are 0603s. So they are small but not ridiculously small like 0402s, or even at work they use 0201s. Those are just minuscule. This is, you can still put them by hand. The little SMC connectors for RF. What else? Yes. And I got two versions of the BFS 17. So unfortunately I could not find the BFS 17 that I had modeled with. So those are from other vendors, so they know it's BFS 17, but it's not the same thing. So one is a lower speed, 1 gigahertz kind of transition frequency, and another one is 3.2 gigahertz transition frequency, which might be a blessing or a curse. The curse is that they have a lot of gain at super high frequencies, so they can easily transform into oscillators. So we'll see which one will work. So these are my SMA to SMC, so I can actually test the circuit with regular connectors. So alright, don't laugh, this is my first experience with solder masks, but I have seen it helps to make a little frame with other PCBs, and so everything is at the same height. So this is really so that your mask is nice and flat. And then I should do it. There we go. Then I realized I made a semi-boo-boo. I ordered them with solder already pre-tinned, and I should have just left them gold. I didn't think very much, but no, it's just less pretty, and I have a little bit of an uneven surface to start with. So since I have the better eyes here, I'll just use the microscope to align it. And don't laugh at me, I'm really not equipped for doing this kind of solder paste work, so I'm improvising. I use a nice PCBWay credit card. Let's see if I can spread the paste. Alright, it doesn't look like too difficult a process. And how does it look on the microscope? Perfect! Okay, here we go. Okay, I'll know that for next time, so here it is. And it looks like I have solder paste on all my little islands, so I'm good. So here we go, I have all my surface mount components. The only slight mistake I made is I don't have the right pattern for transistors, but I still will work. It's just the pads are a little narrow compared to where the pins are, at least for that transistor. Okay, next step, I will be using my hot plate because I have one. I don't think it's a mandatory step, but it makes it easier. And it's set at 120 degrees Celsius. It has been cooking for a couple of minutes, so should be good to go. 375. Okay, the first one of my little board is finished. That's the input, non-delayed. I'm going to get the delayed out and the non-delayed out re-amplified. Alright, so it's time to test our little board, and for that I have to bring the old lady of oscilloscope, the 78754 from Tektronix, because modern scope is not fast enough for what we want to do. So we're going to put the sampling head in, and that's the first scope that I touched in my life, in my baby engineer life, that would do 10 gigahertz. And right now it has the TDR head on it, so we don't want that. The trigger head, here we go. And of course we are going to test it with the fastest pulsar in the house, which is the half repaired 8082A. And I have put the shortest pulse, which is about 2 nanoseconds, on the sampling scope, and it's being sampled. There it is. You have it. 10 nanoseconds, 5 nanoseconds per division, 2 nanoseconds per division. And it has some artifacts to it, and that's because it's a repetitive measurement, it scans, so if there's some jitter, and it looks like there's repetitive jitter in the signal between the trigger and the pulse, it will do this kind of things. But you just do an average measurement, get rid of that. And here you go, at 2 nanoseconds, you say it's exactly within spec, it's a 1 nanosecond rise time. So we are approaching the big moment here. I have hooked up the circuit. I am just coming in from right here with my 2 nanosecond pulse and see if I get the inverted pulse. And turn the thing on. Aha! And we do get something. We get a positive pulse with the wrong amplitude, but the circuit is definitely fast and doesn't oscillate. It's just I have the wrong settings somewhere. And I put my second board, so this is the one we just tested, is the other one, and it's exactly similar. So the pulse inverted, it's plenty fast, but it has the wrong amplitude here. So I might have gotten my resistor wrong, the one I tweaked. Maybe I shouldn't have tweaked them. So I think this is perfectly normal. I'm a doofus. So what's happening is just that I'm measuring it not on 50 ohms, but on 50 ohms in parallel to 50 ohms, which is on my instruments, around 25 ohms. So I've added my termination resistors here, and then of course, then I get half the voltage, right? So I get something that looks like my 300 millivolt. So what just happened is another classic RF design boo-boo. I am measuring the voltage across a 50 ohm collector resistor using a scope with a matched 50 ohm impedance. So I'm basically loaded with 25 ohms when testing and getting half the voltage out. Question is the instrument also going to load the circuit with an additional 50 ohms? I did not think about it, but I'd say quite possibly yes. If so, I should double the voltage swing of the circuit. Alright, so the plot thickens because in the meantime I've been able to get an original manual, and on the original manual you can actually have a readable schematics of what's in the original U2 circuit, and you can see that I'm on the right track. You see the gates internally, they have the 50 ohm termination and the 270 ohm tail resistor on the emitters, but on the output stage it's different. They have 100 and what is it? It's minuscule. 135 ohms, so about half of what this to do the double voltage, and there is no 50 ohms inside the circuit. Actually, it's outside. There is on the PCB, there's a 50 ohm resistor. The output stage have double the swing. So if I do it over here, and I'm going to change this one to 135, and that should double my amplitude if Ohm's law still work, and it does. So now I'm back on my feet, right? And I'm back on 600 millivolts, so that's why they lower that one. It doesn't seem to be affected by the bias. I'm still clean. The simplest thing would be to put the 135. I don't have one, so I might just piggyback two resistors on top of each other just to try. Okay, slightly acrobatic, but I don't know if you can see there. Two resistors on top of each other, and that should bring me down enough so that my amplitude is larger. Okay, try again with the lower emitter resistor, and oh, so the amplitude has doubled, but I have a long tail, so I might have to adjust my bias a little down. Okay, one more time with feeling. I adjusted the bias point down by changing the resistor from 1K to 600 ohms, and well, should be all good to go. There we go, that fixed it. So maybe actually I might have gotten a little too low, but that's a nice 2-second pulse the other way around, and then let's try the other polarity. And that should be the non-inverted one. Yay! Okay, so I went a little too far, and now the rising edge is a little bit lazy, so I have to just order the right resistor. And I made the same modification on the second circuit with the other transistors, supposedly the slower ones from the other vendor, but it looks better. Here's a pulse. This is picture perfect. This is my inverted recreated pulse, and let's see if we can get the straight pulse. Try it again. Oh yeah, this is much better. Alright, so I'll use that circuit in the pulsar. So the idea is that the circuit will go somewhere in here, right, and I will reroute the cables so they go through the extra gate. So assuming I did this correctly, mount this like that. And then that's my ND out, so that's the output that's still working. Goes in here, yeah, it reaches just perfect. And that's it, we are ready to plug it back in. Well, the square wave still goes here. The non-delayed pulse gets re-amplified to non-delayed out and creates the delayed out, so the two original cable that were here, now they plug here. So it's really a super clean repair. It's just a little added board, and we should be all good to go. Okay, so moment of truth, and we just turn it on, and we have two pulses. Yes. So with a little bit of change, I can now delay the second pulse. Yes. Ooh, sweet. There we go. So we have recovered the full functionality. Now if I do single pulses, and let's make sure that our single pulse is still fast enough. Yes, it is. Now I could delay it. Hey, yeah, now I can move it. So here we have it. I think we have fully repaired our pulsar with a little bit of RF engineering, which was a lot of fun. So it's fully repaired now. We can remove the warning stickers. It says it only operates in double pulse mode? Nope. And the delay didn't work? Nope. Everything works now. This is all working as Dave and Bill intended. And give me a nice double pulse. If it could focus on it, that would be better. Come on, there we go. Nice double pulse with controllable delay, controllable whiz, and controllable rise time and the trailing edge time. So that was pretty nice. Our 8082 pulse generator is repaired fully the hard way.